This video begins section 9.8. It talks about the concept of resonance. The definition of resonance is basically if you have one or two or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. For example, if you have ozone, O3, and you were to do the Lewis structure of ozone, you would get something that you see here on the left. Or you could get something like you see on the right. They're both exactly the same. They both satisfy all the rules. The only difference is where that double bond is placed. We can put that double bond at either end of the molecule and show two equivalent Lewis structures for ozone. And if I was to ask you, which one would you expect, the single bond or the double bond, to be shorter? Well, we learned a little while ago that single bonds are longer than double bonds. So you would tell me, well, if we were to measure these two molecules, then you would be able to see a difference between that single bond and the double bond. But in reality, when we actually do measure these bonds in the O3 molecule, you don't. As a matter of fact, experimental evidence shows that both oxygen to oxygen bonds are equal in length. So both the double bond and the single bond are the same length, which happens to be 128 picometers. So how can we resolve this discrepancy? Because single bonds are known to be longer than double bonds, but when we go ahead and measure this molecule, it all seems the same. The only way that we can explain that is through what we call resonance. Resonance itself, that word, means that the use of two or more Lewis structures to represent a particular molecule. So in reality, this is a molecule that has two familiar but non-existent structures. A common misconception about resonance is that basically the molecule is shifting, like that double bond is shifting really quickly, back and forth, back and forth, back and forth from one structure to another. But that's not the case. Neither resonance structure adequately represents the actual molecule, which basically has its own unique, stable structure. Resonance is just something that we humans invented. We designed this term resonance structure to help us with the limitations that we have to be able to explain this. So again, when a molecule has resonance, that means that you can have two different Lewis structures which both satisfy all of the Lewis structure rules, and formal charges are exactly the same on both structures, but all you're doing is moving around a double bond. Because if I move it from the left side to the right side, it's still the same formal charge, it's still the same molecule. Both of them still have the same everything. Let's try to do this for the carbonate ion. So carbonate is CO3 2-. If I went ahead and did my Lewis structure, I would come up with something like this. You have this carbon in the middle, and then you have your oxygens all around the carbon. You notice that two of the oxygens end up with negative charges. That's where your 2- comes from. But if you think about it, the double bond in my first one has the double bond in the middle oxygen. Couldn't I go ahead and just shift that double bond to the left and show this instead? And couldn't I, with the same argument, shift that double bond to now the oxygen on the right? It's all the same molecule. They all have the same formal charges. They all have the same everything. They satisfy all of the rules. And again, according to experimental evidence, all carbon to oxygen bonds in the carbonate ion are equivalent. They're all the same length. And that's why the properties of the carbonate ion are best explained by considering this idea that humans have made up called resonance. Let's go ahead and do a problem. This is problem 9.56 in the back of your chapter. It says draw 3 reasonable resonance structures for the OCN- ion. And then you have to also show formal charges. Okay, so we start with what we know. We got to count up everybody's electrons. Oxygen is 6, carbon is 4, nitrogen is 5, but we got that one extra, so it's a total of 16. Which one goes in the center? Carbon does. So I go ahead and put my skeletal structure. I put carbon in the middle, oxygen on the left, nitrogen on the right. I ask myself, how many do they originally come with? Well, oxygen comes with 6. It's sharing 1 right now, so I'm going to go ahead and put 5 around the oxygen, 2 more around carbon, and 4 more around nitrogen, but I'm going to have to put an extra one because it's a anion. So I'll go ahead and put it on the nitrogen. Right there I can see that I can combine the two lone pairs, one from oxygen and one from carbon to make a double bond, and then the other one from carbon and the one from nitrogen to make a double bond. Basically it looks something like this. You've got carbon making two double bonds with each the oxygen and the nitrogen. Now we have to count up to make sure that we've accounted for 16 electrons. And if you do, you can see that it does. It's 2, 4, 6, 8, 10, 12, 14, 16. Everybody has a complete octet. Let's find out who has the negative charge. If you notice, nitrogen has 1, 2, 3, 4, 5, 6 around it. It's supposed to have 5, so nitrogen carries the negative charge. If we do our little formal charge table, valence electrons that they come with originally is 6, 4, and 5. For oxygen, carbon, and nitrogen. Oxygen currently has 6 around it, carbon currently has 4 around it, but nitrogen has 6 around it. So 5 minus 6 would be -1. So another thing I want to mention is that the formal charge, the sum of the formal charge, should be equal to charge on the ion. So whatever resonance structure you give, once you find your formal charges, it should be equal to the charge on the ion. Okay, so that's one resonance structure. Can we think of another one? What if I go ahead and put one more bond between carbon and nitrogen, making that a triple bond? So if I do that, then I'm going to take the lone pair from the nitrogen and put it between carbon and nitrogen. If you notice, I can't keep it like that because carbon would have 5 bonds around it. So I'll go ahead and move the double bond that was between the carbon and the oxygen. I'll move that lone pair to the oxygen. Now let's see if that works. Do we have 16 electrons around this? We do. If you count, there's 3 lone pairs on oxygen, and the one that it's sharing, that's 8. And then carbon has also, it's got 4 bonds, so that's 8. And nitrogen also has 2, 4, 6, 8. Let's see if we have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay, let's see what the formal charges are. Right now, carbon has 3 lone pairs and one that it's sharing, so that's a total of 7. It came, valence electrons originally is 6, but right now it's got 7, so that's a -1. Carbon came with 4, it has 4, so that's a 0. Nitrogen came with 5, and it has 5 electrons around it, so that's a 0. So this is another resonance structure that we could do for this OCN- ion. This one would put the negative charge on the oxygen. What if I move the triple bond over to the other side? If I do that, then I've got carbon and oxygen with 3 bonds. Oxygen still needs an octet, so I'm going to go ahead and just keep one lone pair in oxygen, and I'm going to make the carbon and nitrogen a single bond. Well, if I do that, then the nitrogen does need to fill its octet, so I'm going to put 3 lone pairs around it instead of the lone pairs around oxygen like we did on the one before. Let's see, first of all, if this makes sense. Do we have everybody with a filled octet? Oxygen has 2, 4, 6, 8. Carbon has 4 bonds, so that's 8. And nitrogen has 2, 4, 6, and then one that pair that's sharing, so that's 8. Okay, do we have 16 electrons? 2, 4, 6, 8, 10, 12, 14, 16. We have 16 electrons. Okay, so let's see what the formal charges are for everybody here. Oxygen comes with 6 originally, but right now it's got 5. So that's going to be 6 minus 5 is 1. Carbon comes originally with 4, and now it's got 4. And what about the nitrogen? The nitrogen comes originally with 5, but has 1, 2, 3, 4, 5, 6, 3 lone pairs, and then 1 that it's sharing. So that's a total of 7. So 5 minus 7 is -2. Remember, the charge on this ion is -1. But what is -2 plus 1? It's -1. So this would work as well. If I asked you, between these 3 resonance structures, which one would be the most important resonance structure? I mean, they basically all give you the same formal charge. They all follow the same rules, but which one do you think is the most important? Remember, the rule for formal charge is that if you have more than one structure and they all have the same formal charge total, right? And they all have -1 here. You would put the negative charge on the most electronegative atom. The most electronegative atom out of all these 3, oxygen, carbon, and nitrogen, is oxygen. But again, These are resonance structures, so they're all plausible structures. If we were to go ahead and try to measure the bond lengths between these three structures, we would see that they're all the same because they all represent the structure. The real structure is something in between all of these three that obviously we do not have the technology to actually figure that out. All right, the last thing I want to talk about is exceptions to the octet rule. So far, all the molecules that we have done have followed the octet rule, but there are exceptions, and there's not a lot of them, but there are some. The first one I'm going to talk about is the incomplete octet. There's some compounds that the central atom is stable even though it does not have 8 electrons around it. For example, beryllium. The electron configuration of beryllium is 1s2, 2s2. In the gas phase, beryllium hydride, which is this, BeH2, actually exists as discrete molecules, so it's stable. The Lewis structure of beryllium hydride looks like this, and as you can see, there's only 4 electrons around that beryllium atom, and there's really no way to satisfy the octet rule for beryllium in this molecule. Some elements in group 3A, particularly boron and aluminum, also tend to form incomplete octets. For example, boron trifluoride, if you count up all the electrons, it's 24 electrons, and there's really nowhere to put it besides around the fluorines. I do want to point out that although boron trifluoride is stable, it does readily react with other things, for example ammonia, to make BH4-. So they do exist discretely, but some of them are not as stable as others, but these two are pretty stable. Alright, let's talk about the next one. There's odd electron molecules. For example, nitric oxide has 11 electrons. These guys are called radicals because obviously you can see that there's an electron that's not paired up. And these are actually really reactive. What's the reason for this, for these unpaired electrons? Is basically to form a covalent bond with another unpaired electron in another molecule. So they're super reactive and they tend to react with other things to make it more stable. The last type of exception I want to talk about is the expanded octet. Expanded octets can only happen to atoms in the third period or beyond. And the reason these things happen is because those in the 3s and the 3p orbitals, they have those available 3d orbitals that can be used in bonding. So for example, something like sulfur hexafluoride, SF6, has 48 electrons if you add everybody up. And look at how the Lewis structure looks like. If you can see, the sulfur has 2, 4, 6, 8, 10, 12 electrons, or 6 bonding pairs that are around the sulfur. But sulfur atoms don't always have expanded octets. They do form compounds which do obey the octet rule, and we've seen some of those, but one of them is sulfur dichloride. If you do the Lewis structure for sulfur dichloride, it follows the rule that we're used to. These exceptions, don't get too stressed out about them. There's not a lot of them. I've shown you basically the ones that are the most important. It's beryllium, boron, aluminum is another one that has an incomplete octet, and then you have these odd electron molecules. It's usually something that's connected with nitrogen because nitrogen has 5 valence electrons. And the expanded octet, which is usually sulfur or phosphorus. Those are the ones that we're going to really be talking about. Okay, so one thing I wanted to point out is I am going to put a animation on Blackboard that deals with resonance, so you guys can look at that. But that's it for chapter 9. I'll see you later. Bye.